Welcome back. In this video, you will learn how to find the arc length of curves using definite integrals. Let's get to it. Alright, so another application of definite integrals is the ability to find the arc length of curves. Alright, so consider this graph right here where we have the function y equals f of x. Let's say that we wanted to know the length of the curve from a to b on this function. How would we find that arc length L? Well, what we can do is by using a definite integral is we can add up an infinite number of very small line segments that together would make up the entirety of this curve. So for example, if we were to look at one particular line segment, such as this one right here, that would represent one of the many line segments that we could use to represent the entire length of this curve. We could find the length of that line segment by using the distance formula, which is a formula that you might be familiar with from algebra. And what that formula allows us to do is if we know the coordinate points of the two endpoints of our line segment, we can find a distance between those 2 points. And so if this point is x sub 1 comma y sub 1, and this point is x sub 2 comma y sub 2, then the distance between those points, or the length of this line segment, would be the following. We would have that the distance is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Right, so this is the distance formula that you most likely learned in algebra that allowed you to find the distance between 2 points or the length of a line segment. And this formula is derived from the Pythagorean theorem, which lets you solve for the hypotenuse of a triangle, which is essentially what we are doing here when we are finding the length of that line segment. Right, so if we were to look at the change in the x value and the change in the y value between each of these points, you would see that that forms a triangle where the line segment is the hypotenuse and the change in y and the change in x would be the other two sides of that triangle. So that's kind of how this distance formula works. It takes the change in x, squares it, adds it to the change in y, squares it, and then takes the square root, and that solves for that hypotenuse or the distance between those 2 points. And so what we can do here is if we label the change in x with dx and label the change in y with dy, we can substitute those into our distance formula and then integrate that distance from a to b, and that will give us the length of the entire curve. Right, that would add up an infinite number of lengths of small line segments that would make up the entirety of this curve. And so if we were to do that, we could say that the arc length L is equal to the integral from a to b of the square root, and this is where the distance formula comes into play. We'll have the square root of the change in x squared plus the change in y squared. So remember, we're representing the change in x in this case with dx and the change in y with dy. And so what we'll have is the change in x dx squared plus the change in y dy squared. And this will represent the arc length L of this curve from a to b. Now, while that is true, we can actually simplify this a little bit into a more usable form that we can use to calculate arc length. And so what we can do is manipulate this integral a little bit by pulling out dx squared out of each of these terms, right? So if we divide each of these terms by dx squared, something cool is going to happen. And so let's take a look. This will be equal to the integral from a to b of the square root of dx squared times 1 plus dy squared divided by dx squared. All right, so what happened here is I pulled out dx squared out of each of these terms. So I divided each term by dx squared. And so when you divide dx squared by itself, you're left with 1. And when you divide dy squared by dx squared, you have dy squared divided by dx squared. Right, so if you were to multiply dx squared back through this quantity, you would end up right back up here where we started. So this is the same as this expression up here, it's just written a little bit differently. But then what happens here is we are taking the square root of 2 terms being multiplied together, and so since this dx is squared, we can actually take the square root of that and pull it outside of the square root. So this will be equal to the integral from a to b of dx times the square root of 1 plus dy squared divided by dx squared. Now I'm going to rewrite this to have dy divided by dx squared, since both the numerator and the denominator are being squared. So we will have dy divided by dx squared. Right, so all we did was take the square root of this term, which leaves us with dx, and so that can come outside of the square root. And now we can reorder our integral and move this dx to the back, and what we'll have is that this is equal to the integral from a to b of the square root of 1 plus dy divided by dx squared times dx. Okay, and so now we have a more usable integral that will allow us to calculate the arc length of a curve from a to b. Now notice that we have dy dx. Do you recognize what that is? Well, dy dx is the derivative of y with respect to x. And so dy dx is the derivative of our function that we want to calculate the arc length for between two particular values of x. And so we could also rewrite this formula to be equal to the integral from a to b of the square root of 1 plus f prime of x squared times dx. And so this right here is what you will typically see as the formula for calculating the arc length of a function f of x from a to b using a definite integral. All right, so if your function is given to you in terms of x, and you want to determine the arc length between two values of x, this is the formula you want to use. However, if you're given a function in terms of y, for example, if you're given that x equals g of y, and you want to determine the arc length between two values of y, let's say from y equals c to y equals d, then you would have a very similar formula that would look like this. The arc length would be equal to the integral from c to d of the square root of 1 plus g prime of y squared times dy. Okay, so if you were given a function in terms of y instead of in terms of x, and you're given two values of y that you want to calculate the arc length between, then you could use this version of this formula. And so to summarize, here are the two arc length formulas you need to know. They're pretty much the same formula, except one is in terms of x and the other is in terms of y. If we're looking at a function y equals f of x, and we want to calculate the arc length of that function from a to b, which are two values of x, then the arc length is equal to the integral from a to b of the square root of 1 plus the derivative of that function squared times dx. But if we're given a function x equals g of y, and we want to calculate the arc length between two values of y, c, and d, then the arc length is equal to the integral from c to d of the square root of 1 plus the derivative of g of y, g prime of y, squared times dy. Alright, so now that you've seen where the arc length formulas come from, let's look at some example problems where we use these formulas. Alright, so here's our first example. We want to find the arc length of the line f of x equals 2x plus 1 from x equals 0 to x equals 3. Alright, so let's start by writing down our arc length formula. We know that the arc length is equal to the integral from a to b of the square root of 1 plus f prime of x squared times dx. Right, since our function is given to us in terms of x, we are going to use the arc length formula that is also in terms of x. Okay, so all we have to do to set up this definite integral here is to take the derivative of our function. And so f prime of x will be equal to the derivative of 2x plus 1. Now the derivative of 2x is just going to be equal to 2, since the derivative of x to the power of 1 is just equal to its coefficient, which is 2. And then the derivative of 1 is just 0, since the derivative of all constants is 0. So f prime of x in this case is just equal to 2. All right, and so now we can set up our definite integral. The arc length will be equal to the definite integral from a to b, which in this case will be from 0 to 3. Those are our two values of x that we want to calculate the arc length between for our function. So our lower bound is 0, and our upper bound is 3. And then we'll have the square root of 1 plus f prime of x squared. And we found that f prime of x was 2, and so we will have 2 squared times dx. All right, and so now we have a pretty simple definite integral that we can solve. And so this will be equal to the definite integral from 0 to 3 of the square root of 1 plus 4 times dx. But 1 plus 4 is just equal to 5, so we will have that is equal to the square root of 5 times dx. All right, and so now we can integrate. The integral of a constant, like the square root of 5, is just going to be equal to that constant times the variable of integration, which in this case is x. And so this will be equal to the square root of 5 times x evaluated from 0 to 3. And so now, all we have to do is plug 3 into this expression and then subtract plugging 0 into this expression. And so this will be equal to the square root of 5 times 3 minus the square root of 5 times 0. And the square root of 5 times 0 is 0, and so our final answer is that the arc length is equal to 3 times the square root of 5. That is the arc length of f of x from x equals 0 to x equals 3. All right, let's look at another example. So for our next example, we want to find the arc length of the curve g of y is equal to 2/3 times y minus 1 to the 3/2 power for 1 less than or equal to y, which is less than or equal to 9. Okay, so what we want to do here is calculate the arc length for this function from y equals 1 to y equals 9. So in this case, we're going to be working in terms of y, since we are given a function in terms of y, and our two bounds are also going to be values of y. And so we will use the arc length formula that the arc length is equal to the definite integral from c to d of the square root of 1 plus g prime of y squared times dy. Okay, so in order to set up this definite integral, we need to take the derivative of our function g of y. All right, so g prime of y will be equal to the derivative of 2/3 times y minus 1 to the 3/2 power. Now, taking a derivative of this is going to require the chain rule because we have a composite function of y minus 1 quantity to the 3/2 power. And so what we'll do is we'll take the derivative of the outside function and then multiply by the derivative of the inside function. And so let's start by using the power rule. We'll multiply this exponent down and then subtract 1 from that exponent. So we'll have 2/3 times 3/2 times y minus 1 to the 1/2 power. Right, we multiplied 3/2 down, so we have 2/3 times 3/2, and then we subtracted 1 from the exponent, and 3/2 minus 1 is 1/2. Okay, so now we want to multiply by the derivative of the inside function, and the derivative of y minus 1 is just going to be 1, right? The derivative of y to the first power is just equal to its coefficient, which is 1, and the derivative of negative 1 is 0, since that's a constant. And so we're just multiplying by 1 here. And now we can simplify. 2/3 times 3/2 is just equal to 1, right? These 2's will cancel out and these 3's will cancel out. And so what we have is that this is equal to y minus 1 to the 1/2 power. And you could rewrite that to be equal to the square root of y minus 1. Okay, so this right here, the square root of y minus 1, is the derivative of our function g prime of y. And so now we can plug that into our arc length formula and then plug in our bounds of integration, which will be y equals 1 and y equals 9. And so our arc length is equal to the integral from 1 to 9 of the square root of 1 plus the square root of y minus 1 squared times dy. All right, so all we did was plug in our bounds of integration, which were given to us in our problem, and then we plugged in our derivative g prime of y, which was the square root of y minus 1, and so we have that right here. Okay, and so now we can simplify. Note that if you square a square root, they cancel each other out, and so we're just going to be left with what is inside that square root function. And so this will be equal to the definite integral from 1 to 9 of the square root of 1 plus y minus 1 times dy. And now we have a positive 1 and a negative 1, and so those are going to cancel out. And so what we'll have is that this is equal to the integral from 1 to 9 of the square root of y times dy. All right, and so now we have another simple definite integral that we should be able to solve. And so if I clean up my work here a little bit, note that we can rewrite the square root of y to be y to the 1/2 power. So I'm going to do that real quick. That will make it easier to take the integral of that term using the power rule of integration. So we'll have y to the 1/2 power. And now, if we add 1 to that exponent and then divide by that new exponent, we will have taken the integral of that term. So this will be equal to y to the 3/2 power divided by 3/2 evaluated from 1 to 9. Now remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction, and so this will be equal to 2/3 times y to the 3/2 power evaluated from 1 to 9, right? The reciprocal of 3/2 is 2/3 if we swap the numerator and the denominator. And now if we plug 9 into this expression and then subtract plugging in 1, we will have our final answer. So I'm going to clean up my work one more time, and now we'll have room to finish this evaluation. So this will be equal to 2/3 times 9 to the 3/2 power minus 2/3 times 1 to the 3/2 power. Now note that the 3/2 power is the same as taking the square root of a number and then cubing it, right? We could rewrite this to be equal to 2/3 times 9 to the 1/2 power cubed. And then we would subtract 2/3 times 1, since 1 to the power of anything is just equal to 1. Okay, and so 9 to the 1/2 power, or the square root of 9, is equal to 3, and so this is equal to 2/3 times 3 cubed minus 2/3, and 3 cubed is equal to 27, and so this is equal to 2/3 times 27 minus 2/3, and then 2 times 27 is 54, so this is equal to 54/3 minus 2/3, and so then 54/3 minus 2/3 will be equal to 52/3. And so that will be the arc length of this function from y equals 1 to y equals 9. Okay, let's look at one more example for this video. Alright, so for our last example, we want to find the arc length of the curve y equals 3/2 times x to the 2/3 power over the interval 0, 8. Alright, so since we're given a function in terms of x, we know that we're going to be using the arc length formula in terms of x, and so the arc length is equal to the integral from a to b, which are two values of x, of the square root of 1 plus f prime of x squared times dx. Now in this case, we could rewrite f prime of x to be dy dx or y prime, since our function is given to us as y equals 3/2 times x to the 2/3 power. So the derivative of that will be dy dx or y prime. It doesn't matter how you express that in your formula, just know that what you're squaring here is the derivative of the function that you are given. Alright, so that's the first thing that we want to find. We want to find dy dx for this function. So we will have dy dx is equal to the derivative of 3/2 times x to the 2/3 power. So now we'll use the power rule for differentiation here. We'll multiply the exponent down and then subtract 1 from the exponent. So we'll have 3/2 times 2/3 times x to the negative 1/3 power. Right, so we multiplied 2/3 down to have 3/2 times 2/3, and then subtracting 1 from that exponent, 2/3 minus 1 is equal to negative 1/3. All right, and so then if we simplify, 3/2 times 2/3 is just equal to 1, since these 3's will cancel out, and so will those 2's. And so all we're left with is that dy dx is equal to x to the negative 1/3 power. Okay, and so now that we have our derivative, we can plug that into our arc length formula and replace a and b with our bounds of integration, which will be 0 and 8. And so we'll have that the arc length is equal to the integral from 0 to 8 of the square root of 1 plus x to the negative 1/3 power squared times dx. Okay, and so if we simplify, this will be equal to the integral from 0 to 8 of the square root of 1 plus x to the negative 1/3 power squared. And so we're just going to multiply those exponents together. So negative 1/3 times 2 is negative 2/3. So we have x to the negative 2/3 power times dx. All right, and so now we have our integral simplified, but it's not entirely clear how we're going to integrate this function. Right, we have a composite function, so we probably want to use u substitution, but if we set u equal to that inside function, note that the derivative of that function is not also found in our integral. Right, when you use u substitution, you need to be able to identify a function and its derivative. However, in this case, that doesn't seem to be possible, at least at first. What we need to do is manipulate this expression a little bit. And at first, when you see this, you're probably going to ask yourself, how would I know to do that? But you'll start to see a pattern with these arc length problems that when you get an expression like this that you're not entirely sure how to integrate, that manipulating the expression like we're going to do here is actually a pretty common technique that you're going to want to be aware of. And so what we're going to do here is we're going to divide each of these terms by x to the negative 2/3 power. Right? We are going to pull this out of both of these terms. So if we do that, this will be equal to the integral from 0 to 8 of the square root of x to the negative 2/3 power times 1 divided by x to the negative 2/3 power plus 1. And that's multiplied by dx. Right? So what we did is we pulled out x to the negative 2/3 out of each of these terms. So if we divide 1 by x to the negative 2/3 power, we have this fraction right here, 1 divided by x to the negative 2/3 power. And when we divide x to the negative 2/3 power by itself, we're left with 1. Okay? And so now what's going to happen is we can take the square root of this term. Since we have two factors being multiplied together, we can take the square root of each of them individually and multiply their square roots. And so the square root of x to the negative 2/3 power is x to the negative 1/3 power, right? It's the opposite operation of what we did right here when we squared x to the negative 1/3 power. We got x to the negative 2/3 power, and so if we take the square root of that, we get back x to the negative 1/3 power. And so we could rewrite our integral to be equal to the integral from 0 to 8 of x to the negative 1/3 power times the square root of this quantity. Now what I'm going to do is rewrite this by moving this x to the negative 2/3 power to the numerator so that the exponent is positive. And so what we'll have is x to the positive 2/3 power plus 1 times dx. Okay, so I hope that made sense what we did there. We took the square root of this term to get x to the negative 1/3 power, but we still have the square root of this quantity, which I just rewrote by moving this negative exponent to the numerator, so now it is positive. All right, so now if we clean up our work here, this integral that we now have can be solved using u substitution. Manipulating our integral in this way has now made it so that if we set u equal to the function inside the square root function, the derivative of u is now also in our integral, right? So if we set u equal to x to the 2/3 power plus 1, and we take the derivative of that, so we'll have du dx is equal to 2/3 multiplied down and then subtract 1 from that exponent, we'll have 2/3 times x to the negative 1/3 power, right? Because 2/3 minus 1 is negative 1/3. And then if we take the derivative of 1, 1 is just a constant, so the derivative is 0. So du dx is equal to 2/3 times x to the negative 1/3 power. But now if we solve for du by multiplying both sides by dx, we'll have that du is equal to 2/3 times x to the negative 1/3 power times dx. Now whatever du is equal to, we want to be able to find that in our integral so that we can replace it with du so that our integral is rewritten in terms of u. And so we're going to be looking for a 2/3 times x to the negative 1/3 power dx in our integral. And I see x to the negative 1/3 power and dx, but I don't see this 2/3. So I'm going to divide both sides by 2/3, and then we'll have a term of du that is equal to something that we can find in our integral. And so dividing both sides by 2/3 is the same as multiplying both sides by 3/2. And so we'll have 3/2 times du is equal to x to the negative 1/3 power times dx. And so now we can replace x to the negative 1/3 power times dx, which is right here in our integral, with 3/2 times du. Okay, so now we can rewrite this integral in terms of u, and so we'll have that this is equal to the integral from 0 to 8 of the square root of u times 3/2 times du. Okay, so we replaced x to the 2/3 power plus 1 with u, because that's what we set it equal to, and we replaced x to the negative 1/3 power times dx with 3/2 times du right here. All right, and so now if we pull this 3/2 to the outside of the integral, this will be equal to 3/2 times the integral from 0 to 8 of the square root of u times du. And now we have a pretty simple integral that we should know how to solve. And so if I clean up my work again, we can rewrite the square root of u to be u to the 1/2 power, and that will allow us to see more easily how we will use the power rule of integration. And so if we add 1 to that exponent and then divide by that new exponent, this will be equal to 3/2 times u to the 3/2 power divided by 3/2 evaluated from 0 to 8. And now remember, dividing by 3/2 is the same as multiplying by 2/3, and so this is equal to 3/2 times 2/3 times u to the 3/2 power evaluated from 0 to 8. And so we can pull this 2/3 to the outside and multiply it by 3/2, and those will actually cancel each other out, right? These 3's will cancel out and these 2's will cancel out. And then we can replace u with what we set it equal to so that we can evaluate this expression from 0 to 8, right? These bounds are still in terms of x, and so we need to rewrite u in terms of x so that we can actually do our evaluation. And so this is equal to x to the 2/3 power plus 1 to the 3/2 power evaluated from 0 to 8, right? We just replaced u with x to the 2/3 power plus 1, so we have that quantity to the power of 3/2, just like how u is taken to the power of 3/2. All right, and so if we clean up our work again, we can evaluate this by plugging 8 into our expression, and then subtract plugging 0 into this expression, and so we'll have that this is equal to 8 to the 2/3 power plus 1 to the power of 3 halves minus 0 to the 2/3 power plus 1 to the 3 halves power. All right, and so then if we simplify, 8 to the 2/3 power is the same as taking the cubed root of 8 and then squaring it. So let me rewrite that. This is equal to 8 to the 1/3 power squared, right? If we multiplied these exponents, we would have what we have right here, the 2/3 power, and then plus 1, and that's still to the 3 halves power, minus 0 to the 2/3 power is just 0, so 0 plus 1 is 1 to the 3 halves power. And then 8 to the 1/3 power is the cubed root of 8, and the cubed root of 8 is 2, so this is equal to 2 squared plus 1 to the 3 halves power minus 1, because 1 to the 3 halves power is just 1. Now 2 squared is 4, and 4 plus 1 is 5, so this is equal to 5 to the 3 halves power minus 1. Now you could leave your answer in this form if you'd like to. This would be your final answer, but note that 5 to the 3 halves power could be rewritten to be 5 times 5 to the 1/2 power, and then you'd have minus 1. Right, you have 5 to the first power times 5 to the 1/2 power. Multiplying them together would get you 5 to the 3 halves power because the exponents would be added, so 1 plus 1/2 is 3 halves. But this is the same as 5 times the square root of 5, and so you could write your answer to be equal to 5 times the square root of 5 minus 1. It just looks a little bit nicer, but once again, this is also an acceptable answer. And so this will be my final answer, but you could also have this as well. Just know that the approximate value, if you were to plug it into your calculator, would be approximately 10.18. But either way, whether you say approximately equal to 10.18, or 5 times the square root of 5 minus 1, or 5 to the 3 halves power minus 1, all three of those would be acceptable answers for the arc length of this curve from x equals 0 to x equals 8. All right, and so with that, that is all I had for this lesson. If you want to see some more example problems, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.